Hello, everybody. Welcome back to Code to Bare Metal. I'm happy to be back after a short hiatus. I've been quite busy with my semester and job search, so just had to take a short little break. But we're back and should be a little more consistent for the foreseeable future. Before we start, I just want to let you all know that there is a community Discord that is in the channel description. I'll also link it in the video description down below. This past weekend we had a great, or it was about a week ago. That weekend we had a great community discussion with a couple of you. Talked a bit just about compilers in general. My compiler, a bit about the job market, and much more. So we'll definitely do some more of those in the future, and I hope to see more of you there because I thought it was really productive and I thoroughly enjoyed it. So today we're going to be talking about the first step of that pipeline that we outlined in the last video. We're going to rehash a little bit of Lexer theory. I won't repeat myself too much, but we will a bit. And then we'll talk about how you might go about actually implementing one. Today we're going to, in addition, introduce a fairly basic syntax that we're going to build a compiler for. We're going to call it Code to Bare Metal Lang, in the spirit of the channel. And as we work through this, and today's going to be the first video, we're gonna really work in pairs of videos. So we'll basically do a first video where I talk about some theory and set you up with a basic framework with functions, things like that. We'll talk about, okay, well, here's a template of what we need to do, and then you will have a week or two to go work on that. In the Discord, there's community discussion channels. I encourage all of you to go work on these together, and then in the next video, I will show you my solution to the problems I posed. So we'll work through that for a Lexer, a parser, a semantic analyzer, and eventually an LLVM code generator, and then we'll have something working. This sort of aligns, I think, with my objective of giving you all the requisite information to solve something, but again, without it just being an outright tutorial, because that's not super helpful, I don't think. And then the solution will serve as my way to illustrate the way that I solve problems, and we'll go through the solutions from that perspective. Because I think that seeing my problem solving approach will be far more useful to you than whatever result we get from, in all likelihood, is going to be a language that can't do much that is unique comparatively to most other languages out there. It's really just a learning language. I encourage you all to go out and expand on what we talk about, extend the language, and make it your own. Because this would be a good opportunity to do that, and you can. That's where you'll learn. That's where you'll learn the most, by taking this information that I give you and building upon it. So today we're gonna talk through the Lexer, of course, as I said earlier. We'll start a bit of a project. I'm going to outline the needed functions, show you how to configure the build process, etc. So as a result, in terms of build, you'll probably learn a little bit of CMake, some bash scripting. I might throw a little bit of Docker in there. That's another tool that's pretty commonplace now and I think is useful for everybody to know. So I think we'll probably throw it in there because it's neat and it can really streamline your build process in a very convenient way. In the next video, we're going to go through two of many, many possible solutions to the problems that I pose to all of you. So I'll show you a Lexer implementation for the Code to Bare Metal CBM Lang in C++ and Haskell. So you get a bit of both worlds because it's possible in both languages, and that's useful. I hope that this structure suits all of you, but please make suggestions as always. I always appreciate feedback. So without further ado, let's begin. All right, so I just had a little bit of a hiccup as I was recording from my iPad here. I did not have my sound on. So we're going to be doing a take two, but I suppose I got some extra practice, so you'll probably get a better version here. So last time I outlined a plausible and common pipeline for what a compiler that leverages the LLVM to be platform agnostic might look like. And for the foreseeable future, we're going to be operating in compiler front end land where we're just getting to that intermediate representation. So let me just redraw that diagram, briefly talk about each step, and then we will get into the Lexers. So, right, we started out with some input. Excuse my handwriting again, please. You're going to go through the Lexer, and this is what we're talking about today, so I'm not going to talk too much about it yet, of course, but right, that's what we're doing. You're going to take that output and you're going to go through your parser. And what that parser is going to do is it's going to take your tokens and generate something called an abstract syntax tree. And I showed you an example last time, but we'll go through that more in depth. I have some nice diagrams I've been working on that should look a lot better because they're digital and not handwritten by me. So then you take that abstract syntax tree and you pass it through your semantic analyzer. And that is a glorified type checker. But frankly, I found that to be one of the most gratifying components of my language because that was the first time I could really look at what I've done and say, wow, this is actually powerful, and it's following modern language conventions, and it has features that you would expect from a production level language, although I'm not there yet, but nonetheless, right? So what you want here is you want to allow things like scoping, variable shadowing, and what you're really the whole idea is you want to validate that your program is type correct and that all of your functions, arguments, etc. are type correct, so that you don't get any weird errors that show up when your LLVM module becomes incorrect because you're putting a string type and an integer type together and you haven't accounted for that, but your semantic analyzer didn't catch that. So LLVM gets confused, and then you get a seg fault, and then you have to run it through Valgrind and read through that, and you just have no idea what's going on, and you're really sad. So that's what this is for. It saves a lot of those errors. And in addition, if I shipped that to somebody and my semantic analyzer didn't catch those errors, and then somebody wrote code and they got a crazy seg fault from LLVM, that's on me as the developer, right? Because I should handle those cases. So very important component. We're going to spend a lot of time there. It's really, really interesting. I'm really fascinated by it. So yeah, stay tuned for that. So once you get through the semantic analyzer, you're going to pass that through your code generator, where you're taking that semantically analyzed AST and converting it to LLVM IR. And then you're going to take that IR and you're going to pass it through the LLVM backend. And that you can do, well, here you can do some optimizations, right? We'll talk some about that later on. It's something I'm exploring. And then once you pass through the LLVM backend, you end up with an executable file for your target architecture, operating system, etc. So this is just a brief review for you all. We're living here today. So yeah, let's start by rehashing some Lexer theory. Okay, so right now, as I always do when I solve problems, when we're talking about what a compiler architecture could look like using the LLVM, we started with our inputs and outputs and worked our way in. Let's do the same thing with the Lexer. Although today, it sort of crosses into that land of implementation details, so we're going to talk a little bit about that, right? Because it gets to a point where I'll probably write some pseudocode, but it becomes hard not to start to implement the thing once you have a good enough grasp on what it actually needs to do. And the Lexer itself is not all that complex when it comes down to it, what it's actually doing. So let's talk about our input and output. So, right, we're taking in an input text file in CBM lang in this case, and you're going to pass it through your Lexer. So we're going to draw it as a circle, I guess, because it's a component, not data. And then we're going to end up with two things. We're going to end up with an array of these things called tokens, and we're going to get an array of associated values. And this is where we're going to talk kind of implementation, high-level details. So I know we walked through some examples in the last video, but let's do it again and let's sort of frame it a little bit differently. So very simple. Let's do an integer declaration. Int a equals, I don't know, 47, right? So this will be, I can tell you, comprised of 5 tokens. So let's walk through what each one of them will look like, and then we'll talk about the output. So this, say, is my input text. So this is just living in a file somewhere, right? So then I pass that through my Lexer here. And what I needed to do is twofold. So first, I needed to say, okay, what are my tokens? So if you look here, right, this is going to be an integer keyword. And that's the bottom line. It's just I see int, I pattern match it. I see, okay, well, I'm looking for int. Well, that's an int keyword. Okay, let's save that as a token. Then I see this thing. In this case, it matches what I will say would be a valid identifier, and we'll define what those are using some regular expressions later. I don't know if you have experience with that, but I'll walk through them fairly slowly and just make sure we understand, because they are quite powerful, and they're not as bad as maybe one might think they are. And yeah, they're very useful. So right, so this is an identifier here. So we would store an identifier token. Then we would store here an assignment token. Here we would store an integer literal token, and here we would store a semicolon token. So that's the first thing. We're going to have 5 tokens. So for this input text file, we're going to have an array here of tokens, and we'll define what that means, and it's going to have length 5. And then what I will tell you here is this is going to also have values, and it's going to have length 5, but it gets a little bit more complicated, so that we'll get to that. So let's talk about what the values need to be for this. So for the integer keyword, that's always going to be an integer keyword. If I read an int keyword token, that's the meaning of that is never going to change, the value associated with that. So how I'm going to denote that here is I'm just going to write 0. Sorry, that's a really bad 0. I don't need to store, and it now looks kind of like 5. Okay, whatever, that's a 0. I don't need to store any related information. Now, with a here, if the whole point of an identifier is to be able to reuse it later. I define a value, I probably want to reuse it in my code somewhere. Otherwise, well, what was the point? So if I just say, well, I have an identifier keyword, but I don't store the value a, I can't reference it later. So the whole point of it kind of is useless. Why not just use raw values? And then you can start asking the question, well, what was the point of making the language in the first place? So I definitely am going to want to store that value a, and it's probably going to be a string. This is not part of the language. I'm just sort of illustrating that. Right, because if you just had single character identifiers, that's not super useful. There's a lot of ASCII characters, but theoretically you want your range of identifiers to be infinite, within a valid what you call a regular language that you can describe with irregular expressions. We'll describe what that means shortly. So, right, so you have that. Then you have this assignment operator. It's similar to the int keyword. You definitely do not need to retain any information about that. An assignment token is always going to be an assignment token. Here with the 47, we definitely want to retain that value. Otherwise, I can't reuse it later, and then it becomes useless. I just have integer literal token, but no value, so we want to store that value. And then the same thing with the semicolon. Definitely don't need to store anything there. Semicolon will always be a semicolon. So moving on, let's talk a little bit about how you might think about implementing these. Now, I'm not going to give you a raw implementation, but I'll give you an idea, and this should work for both functional and the procedural implementation that we will eventually have and work through in the next video. But this should maybe give you an idea of how to start. So at least in C++ and similar in how I did in Haskell, for tokens, you can generally just define those as an enumerated type. So what an enumerated type is essentially you're just storing meaning to integers, and you are enumerating them. And again, I know don't use the name of the word in the definition, but all I mean by that is, so let's just say we have an enum tokens, and I think this is C++ syntax, but that's okay. You might have token, integer, keyword, right? and you'll just assign that -1. And I generally go with negative values, especially for something like this, because you want to at all cost avoid ASCII conflictions if they show up, and ASCII are positive. So generally go with negative values if you can. Not always necessary, but for this example, or for this particular use case, probably a good idea. And then another one, right, that we would have, say, token identifier. That would be -2, and then you just go on so on and so forth, right? So they all just correspond to some integer, but you're assigning some meaningful identifier basically to that integer, so you can reference them in that way, as opposed to the raw integer values later. But nonetheless, the compiler is just storing them as integers. So you would do this for all of these. So say our language just allowed you to make this type of declaration, you would need identifier tokens, integer keyword tokens, integer literal tokens, assignment tokens, and semicolon tokens. So you would have 5 in the CNUM, but this can become a lot more quite quickly. You might have 100 or 200. I don't know. Depends on how much sort of strict given syntax that you allow in your language. But yeah, okay. So that sort of takes care of the tokens, right? But the value is it's a little bit more interesting and a little bit more complicated, because our problem has some layers of complexity. So not only do I need to deal with this, right? So I need to be able to say, well, sometimes I want to store an associated value, but sometimes I also don't care and don't need to. So you could either store maybe some kind of sentinel value there, just like a marker value that says, nope, this is nothing, you can ignore it. But an idea borrowed from functional languages that I think C++, Java, and more all have them now. Just Rust definitely makes use of them. That's where I think I started to realize how powerful they were. Are these things called optional types, and they are amazing. And you should all definitely start using them in your code as much as possible, because they are super powerful. They're memory safe. They don't add that much time overhead. They're just awesome. So all an optional is it encodes 2 possible values: something or nothing, right? That's it. So this is just like memory safe null, basically, and this is something. So that's what we do here, right? So in my value array, I would have nothing here, something here, nothing here, something here, nothing here. So that's the first layer. Now the second layer is, well, oops, apologies. This is a string, right? Identifiers should be referenced as a string, or a character array, whatever you want. Depends on how you're doing this, but let's just say string. Keep it simple. And then an integer here, right? And maybe you want floating point values, booleans, even more complex, crazy literal types that you allow. So how you would do that in a memory unsafe way, and you could argue in an archaic way, would be a union in C or C++. Again, talking implementation a little bit more. But what a union does, if you haven't worked with them, is it allows you to have a data type that can contain a lot of potential, or one of many different data types. So I could define a union like this. I could say union, my union. I don't know if this is valid syntax, but you could have it like an int a and an array. No, because that wouldn't be super useful. And then we could also have it say an integer array with 8 32-bit integers b. Oops, what's going on there? What happened to my computer? Are we still recording? Okay, I don't know what happened there. I guess my computer went to sleep. Okay, so yeah, what's going on here, right, is I can either store one of these in this union, but the size of the union is going to be the size of 8 integers, right? So because basically the size of the union will be the maximum possible, will be the size of the maximum sized data type that you can store in your union. Now, this isn't a video about unions, but they're kind of neat, but they're also not great. You can't really use them for complex data types. They're not super safe. So C++ and many other languages offer this thing. This is how C++ has them. They're called a variant. And what a variant allows you to do is it's very similar to a union, but say I want to have the option to store a string, a character, a boolean, an integer and a floating point number, I can put that right into a variant. So I can say variant, and this isn't the right syntax, my variant, and I can store an int, character, boolean, so on and so forth, right? That is not a closing brace. That is also not a closing brace. So I have that, right? So going back to here, tying this all back together, to have this value array, what I'll do is I will have an array of optionals of a variant, and that variant is going to contain all the possible data types. So functionally, when I want to access a value, I can always extract that information from this array because in a memory safe way, it'll tell me if it's there or not. And in addition, I can store all of these different types. So again, implementation detail, but it's neat and it sort of just illustrates the power that we have as developers and with modern languages. So let's see. I just want to make sure I don't want to say anything more here before we move on. Yes. So one more thing is even though we have this extra wrapper here that is awesome, the nice thing about when we're actually going through this value array is you're only going to be accessing the optional values when you say see an integer literal token in your token stream. But since these are parallel arrays, you're generally not going to have a none value that you're trying to access, because so long as you wrote your Lexer correctly and you tested it and made sure that it works, there should always be something at the point that you're trying to access, because it should directly correspond with a token that should then encode an actual value. I'm sorry, that was a roundabout way of saying that. So if, like, back to our example, int a equals, what was it, 47. Right, I have these two arrays, and these are my tokens. You just break that up into five indices, and then you do the same thing. This is your value array. So here we have nothing, we have nothing, and we have nothing, and here we have a, and we have 47. So I'm not going to write in the tokens here because we've said it through enough times. But integer keyword, identifier, assignment, integer literal, semicolon, right? But when you're going over this array, well, the only time I'm going to be looking for this, right, is when I see something that should correspond to a value in my value array. So again, it's sort of just an extra layer of safety, but yeah, that's the idea. So let's move on before I keep rambling. All right, so I am a bit of a goofball, and I did it again. I accidentally didn't record my voice, but again, you'll probably get a more refined version, so that's always good. So here we're going to introduce code to bare metal language. It's going to be quite simple, but it's really here to illustrate a point and serve as a learning experience for all of you. So what I do encourage you to do is expand on these ideas greatly and build something incredible with the foundation that you get here. In the Discord, I really hope that you all discuss solutions together, work together. Development doesn't happen in isolation. These are difficult ideas, and it can be incredibly rewarding to work with other people who are really invested in the same thing that you are, and probably have different ideas than you do, and to talk about them. That's where the most happens, when you can have a conversation with somebody about something that you're both very knowledgeable about, but you can, when you work together, you can often end up with a better idea than you could come up with in isolation. Just as sort of a housekeeping note, I will post my solutions to the problem either right after I post the next video, where I give the solutions, or just prior. I haven't really decided how I'm going to go about doing that yet. I will link a GitHub repository in the Discord and along with the next video when I do post them, so stay tuned for that. So, without further ado, let us start talking about code to bare metal language. All right, so without further ado, let's introduce code to bare metal language. So, for any language, what you first want to do is consider what you want it to do. For my personal programming language that I'm working on, the Pyroxene programming language, I wanted it to have built-in support for the graph data structure. So I tailored the language towards that and the design. And right, that starts with the Lexer. So when you eventually, if you choose to do so, construct your own language, or if you decide to add extra really cool functionality to CVMlang, you first need to figure out what you want that to be, right? I mean, I know that sort of shit sounds obvious, but you'd be surprised. So for CVMlang, I want it to be a fairly simple language that I can use to illustrate some core LLVM concepts, right? So I'm gonna just write down the broad in broad terms what I want. So first, I want this. So global and local spaces, and what I mean by that is I want variables to exist both globally and within functions, right? So say I have an integer a that's defined in the global scope, and then I have a function, say my function, and I also define an integer a in that space. I want the compiler to know that when I refer to that variable a within that function, that I'm referring to the variable a, I'm referring to the instance of that exists within that function. So isolation of spaces, and this should exist for conditional blocks as well. So if you declare another integer a in an if statement within that function, and then you refer to it in that if statement, the compiler should know which one you're referring to. So second, we want global and local variables, right? So that sort of is a natural extension of what I said before, but you want variables to exist globally and locally, and how those are going to be represented when we get to LLVM is going to be a little bit different. If you've coded in assembly at all, you'll know that global variables are generally declared with a label and a static value that can be modified, but you just refer to that label in your program. But for local variables, they don't actually get a label. They're pushed and popped from the stack, and that stack value is modified based on where it is in the context of the current frame pointer for that function. We will talk about all of those ideas if you don't know what I'm talking about. But functionally, I'm really just explaining or just articulating how function calls really work in assembly. So 3, we want function definitions and calls, and within that, I want to be able to have argument passing, right? That's important. You don't want to just have functions. You want to be able to pass arguments to that function that are dynamic and allow the function's behavior to change based on what arguments you're passing. In addition, I want basic types. So we're going to have integers, floats, characters, and booleans. We might add more complex aggregate data types later, but for now we're just gonna keep it like this. So as an extension of this, we want identifiers for these. So we want to be able to store them in variables, and yeah, they should be able to be reused later, and of course type validated. As another thing, we want conditional logic, and how I'm gonna keep it fairly simple because. Although the first steps are fairly trivial to get, say, a nested conditional where you maybe have if, else if, else if, else if, else, right? Lexing, parsing, etc. It's not too bad, but when you get to the code gen phase, I saw firsthand how nasty that can get and how mangled and spaghettified your IR can get. So we are going to possibly explore that later, but for now we're just going to have basic conditionals like if and then if else, right? So you can have an if in isolation, or you can have an if and then an else statement, right? If that if condition block is skipped over, if that condition is false. I want basic input and output. Um, so how we're gonna do that is we're not going to reinvent the wheel. We're going to build on the shoulders of giants. Turns out you can make calls to the printf and function in C using LLVM, and that will work. And that keeps our compiler platform agnostic, because if I was to write direct system calls to make console input and output to add that functionality, that could get quite complicated quite quickly and is not really in the spirit of what we're doing. Maybe we'll explore that later, but right, we're not really exploring the operating system much here. We're trying to abstract away the operating system, actually. So yeah, that's what we'll do for input and output. We'll do calls to printf and scanf. We want binary expressions, right? So what that means is we want to support operators, so plus, minus, multiplication, the not operator, potentially modulus, maybe the division operator. That depends. Another thing, and this is, we'll probably do a whole video series on this, but this is something we'll probably explore later, is include directives and the LLVM linker. So you can link in dynamically other LLVM modules, so you can combine your files together and make really big programs. So that's really cool, and that's another step that you can take to make your language, that much closer to being production ready and comparable, and fulfill the expectations of what a modern language should be able to support. So the last thing is we want variable shadowing. And that harkens back to what I was talking about with global and local spaces. If you have variables named the same thing, you want to make sure that when you're going to IR, when you refer to them, you are referring to the one that is in the most nested scope. So if you have a global and then a function and then an if statement, and you define variables the same name and the same type, or not the same type actually, you want to refer to the one, say, in the if statement, right? Because that's the most nested scope, and again, that's sort of a modern language feature. So this is what we want our language to do, and this will illustrate a lot of the LLVM concepts. And once you have this, then you should be capable at that point of going out and reading the LLVM docs and figuring out the little nuances to get it to do exactly what you want it to do for your custom language or your custom feature that you're trying to build. So, like I said, this is very simple, but it covers the basics. We might add some aggregate data types later. In addition, I encourage you all to greatly expand on this. Find things you don't like about it and fix them. Talk about it. Tell me about it. Work together and make something amazing out of this. This is just a blueprint. I'm just giving the foundation and trying to facilitate your learning so that you're eventually able to build something that is greater than CBM Lang will ever be. So once we define what we want, we now need to ask, what does our language syntax look like? So we have our ideas here. Let's talk about syntax. So we go over to this file, which is another text file. So first, right, we want variables, right? So we can have those in the forms of declarations and definitions. So keeping that C-like syntax. Again, I love it. Some hate it, but again, you can make your choices when developing this. That sort of comes down to the Lexer, how you're evaluating that input file. So you get that choice today, actually, but you can modify it later. The great thing is we're going to build this in a modular way. So if you want to change how the syntax is processed into tokens, as long as the token stream remains the same for the later steps, it doesn't matter, right? If, say, you don't want braces anymore, or say you want to force indentation or something, you can do that in the step, and it shouldn't change the later steps as long as you're outputting the same token stream, right? So, okay, back to what we were doing. Let's say we want variables, so variable declarations and definitions. So what that should look like is you want a type, and that should be int, float, bool, care, right? Just the basic data types. Then we want an identifier. And then we want either a semicolon or an assignment operator, right? Because it's either a declaration or a definition. And then, again, I love my optionals, but we're going to get an optional of a value and a semicolon, right? So this is optional because if we have a semicolon here, we're done. But if we have an assignment here, we have to have a value and a semicolon to finish that off. Otherwise, it's not valid. The Lexer will say it's valid. In later steps, the compiler will throw an error out at the user because that is not a valid grammatical construct. But today we're not worried about grammar. So the second thing we want functions, right? So this is specifically function definitions. So what I'll say is we're going to say fn is how you declare a function. You again want an identifier. Then you want a return type. And that is again going to be in this form here, one of these. And then following the return type, you want a block, and then you just want a bunch of expressions in there. And those can be whatever you want. Binary expressions, print expressions, variable declarations, so on and so forth. Just a bunch of expressions that do something, maybe a return in there, right? Third, we want conditionals. So how we will describe that is we'll allow if and then some expression, and that is going to be our conditional. So that's going to have to follow some specific syntax, make sure it's a Boolean, right? But that can be checked later. It doesn't have to be checked now. So after that, then you're going to have, again, back to the optional. You'll have an optional else block, which just has expressions. And apologies, I should have had here. What did I do? Nope. There we go. You want an expressions block for the if statement, right? Because you want to be able to do something if that if condition is satisfied. Okay, so now that we have that, we want our input output. So you want print expression or input expression, not expressions, but that it can be binary. We should be able to sort that, or a function call, say. We want binary expressions, so how that is just an expression, then an operator, and then an expression. And then lastly, we want function calls. So how we want that to look like is an identifier, right, corresponding to the function. That can be validated later. We want an identifier, we want a parenthesis, and then we just want our arguments separated by commas. That's sort of commonplace, right? Most functions, unless, well, you'll see when we do Haskell, it's not quite like that. But for C-like languages, Python, Java, so on, whatever, a lot of times it will look like this. So that's how we're going to do it. Okay, so let's just, before we proceed, let's briefly talk about operators. So operators, we will have precedence, and we'll talk about how we're going to go about doing that later. But I want the plus, I want the minus, I want the multiplication, I want the modulus, I want the not, and what else did I say? I think I want the division as well, because it shouldn't be too much of an added, it shouldn't be too cumbersome to add. And I should have added this. I want to allow for comments and white space. This is not super related to the language itself, but it's an important thing to note because we're gonna have to directly deal with that today and in the next video. So then the next thing I want to talk about, the last thing related to direct syntax is I want to bring up not expressions, how we're going to deal with identifiers. And this is where we're going to briefly talk about regular expressions. If you haven't seen them before, I swear they're not evil. And functionally, we want to describe what's called a regular language, which we can describe with a regular expression that describes how all of our identifiers should look. And the pool of possible identifiers should be theoretically infinite strings. So what I will say is, in most languages, what is considered a valid identifier is the first character is alphabetic or an underscore, right? And then all other characters are alphanumeric or an underscore. So you can have basically the first character has to be alphabetic. You can't have a number, otherwise it'll get confused, and that's not good. That would be much more difficult to implement. So instead, we'll say, okay, the first character has to be alphabetic or an underscore, and then it can have 0 through 9 or underscore or capital or lowercase a through z. So yeah, it'll support whatever style convention you want, right? You have snake case, camel case, etc. Pascal case. I'm a big snake case person. I don't know. It's just been grained into me, for better or for worse, but that's what I roll with. So if you look at my code bases, you will see a lot of snake case. Yeah, okay. So let's get back on track here. So I can describe this very simply with a regular expression. So let's see. So for the first character, it's a through z, or underscore, right? And then how I'm going to describe the rest of it is a through z, 0 through 9, underscore, and then I'm going to do something called starring that. And what that means is this is a single character. This is 0 or more characters. That's what the star does to this. So all I'm saying is the first character is alphabetic or an underscore, and then it can be any number of these subsequent characters subsequent to that first character. So as an example, 24 CBM Lang and CBM Lang 2024, right? So this is valid here because it's starting with an alphabetic character or an underscore, but C is alphabetic. And then all of the remaining characters here, B, M through 4, all are alphabetic, numeric, or an underscore. So this is valid. This is invalid, right? Because it's starting with a number, so it doesn't fit this first character here. Everything else is fine, but this is invalidated, so the Lexer would throw an error here. Okay, so I know this is a lot, but based on all of this, let's talk about what tokens we need, because tokens should be fairly general, right? We want to be able to encompass a lot of, we want to be able to encompass all identifiers within one token. So how do we do that? So first, let's say, what are our language keywords? And I'm going to write in caps here. It's not because I'm angry, I just for emphasis. So do not hold associated values. All right, so apologies, continuing. So for keywords, we want all of these. So we want int, float, char, bool. Let's see what else. Fn, if, else, return, print, input. So these are the keywords of our language. They're always going to be the same. An int keyword is always going to be an int keyword. There's no associated value with it, so that's the bottom line. We just need a token that corresponds to each one of these. Then I need my single character tokens. So these are operators, things like that. So these also do not hold associated values. And these are going to be things like semicolon, open close brace, open close parenthesis, equals, addition, subtraction, multiplication, division, exclamation point, comma, modulus, right? So again, no extra information needs to be held within these. They're just sort of standalone, no extra value. They're just a token. So each one of these would get its own token. And the last thing we need is, well, everything else. And actually, we need less tokens for this, even though this is kind of going to describe the bulk of the language. So yes, these do need to hold values, because, right, these are going to be our things like identifiers. So we need identifiers and our literal values. So this was harkening back to what I was talking about earlier. If you have that int a equals 47 semicolon, you need to store the a, right, as a value, but you also need to store it as a token, so it knows that, okay, I have an identifier, and it needs to know that it's an identifier. So you need to figure that out. So functionally, yeah, this is what the Lexer needs to do. It needs to take these, from that input file, it needs to find these, store them as tokens, and then in this case, store them as an associated value as well. So, well, what do? Right, we defined it. We define a token for each of these, and we talked about the enum approach. And I'm gonna set up sort of a template for you all right after this. But yeah, I'm gonna give you some boilerplate, and hopefully you all come up with some really interesting, unique solutions, and I will provide you with my own solutions to this Lexer in the next video. So yeah. Okay, so let's just talk through these templates here that I have created for you to work on these problems. There's 2 of them. If you would like these, I suppose join the Discord and send me a DM, and I will send you a zip file of all of this, and you can run from that. So just a couple of things though. What you're going to need installed, you're going to need CMake, and I believe I have it specified. Let me just check. Yes, you need the 3.30 or greater. You need C++ 17 or newer. C++ 20 is fairly nascent, so I would go with 17. Stable. I would use Clang, because we're working with the LLVM. You should use Clang. If you're on Apple, even if you think you're using GCC, you're probably not. If you're anywhere else and you have GCC installed, try to get Clang. Try and get Clang 17, Clang++. Okay, so yeah, let's just talk through this really quickly, and I will send you all on your way to start this. So yeah, actually, I do have a build script here for you too. So, all right, so if we just look, so first we'll talk about the C++ version, because this is really the version we're going to be working on. The Haskell version is fun. It's a cool exercise, but it's only going to get us so far. Maybe later we'll expand on it, and maybe we'll do something with like serialization, like protocol buffers or something, where we use Haskell to Lex and maybe parse the input, and then convert it into a serialization format that we can then send to C++ to convert to IR. That could be cool, but that is a little bit ambitious, so let's not do that right now. So let's look at these 2 files. So really this is the crux, or actually these 3. This is the crux of what we have. Oh, what happened there? Okay, so what I've defined for you is a header file here. So you just have a couple of things, a couple of functions and a couple of type definitions. So remember that variant I was talking about? It's kind of like a union. So we have this guy here. So I'm calling it the Lexer value variant, right? Be as descriptive as I can be. Change it if you'd like. It's just going to have to change in other places as well. But, right, it can hold either an integer, a floating point number, a character, or a Boolean. So now in place of this, you can just have this guy. And then I define this enumerated type. It's a lot. It's pretty nasty. There's a lot of these tokens, but it's called tokens, and we define one for each of those language constructs we described earlier. So I tried to make the names as descriptive as possible, right? So these are keywords like integer, int, return, if else, print, input. These are some of the single character guys. These are literals. This would be for an identifier. End of file, that's something you do have to worry about in C++. So this is essentially the crux of the output that you're going to be getting here. And then what you will be doing is you're going to work on these 2 functions. You're going to work on this function called getNextToken, and what that function is going to do is it is going to read through the character input, and it is going to read those characters until it sees a token, and it's going to return a token, all the while consuming the input of say, an input file, so that when you go back and call that function again, it'll start from where you stopped. And I'll give you a little hint. Look up getChar. That's a function. Right? You just read directly from it. So yeah, look into that. And I believe it encodes like global states so that it retains its location when you call it again. And then this guy, this is funkier. I swear this is not as bad as it looks, but this is going to tokenize this is what you will use. This should, in theory, keep calling this until you get an end of file token. um, and basically store those into something we can use later. So what this should return is actually not bad. So it's going to be a pair. So it's going to be two vectors, which are just memory safe, dynamically resizable arrays that are generic in C++. So we're going to have a vector of tokens like we talked about earlier. And then I'm glad I talked about it. We're going to have a vector of optional types of our variant that we defined above. So this is going to store a vector of values as needed and a value of none when they're not needed. So I will leave it up to you to figure out, to go read the docs on optionals, and you're probably gonna have to do a little bit on variant too, but it's not that bad. Pair as well, I will just say basically how you would access the first vector is return dot first and then return dot second for the second. It's fairly trivial. So once you grab the return, that's how you would access these values. You don't actually need to access them. I just want you to write the function for now. So yeah, go for that. Please message in the Discord. I don't want to give away too much because I really want to give you the opportunity to mess around with this and see where you can get. So then I just have this nice driver for you. So standard main function. Right now it just prints, yep, we're in the driver function. Make sure, it's just so you can make sure everything's working on your computer and you're getting no compile time errors before you even start. If you are, let me know. Maybe we can hop in a Discord call and troubleshoot that. I know that CMake and the such can be difficult sometimes. So yeah, basically try and maybe read in a file here and call this tokenized file function that you write, and then print out the output or something and see if it's what you expect. Yeah, so that is the C++ version. To do this, I've written this CMake file for you. So this will generate an executable for you. So what you are going to need to do is you're going to need to do a couple of things. So you're going to need to make sure you have these things installed, but also in here, in the C++ directory, you're going to need to do a few things. So first, this build file I will not include because that is very much so local to my computer, and that everything generated in there will not work on your computer unless you own the exact same computer as me with the same configuration, so on it. So yeah, that's not going to be included. So first what you're going to do is do cd or mkdir build if you're on Mac or Linux. You can make a file on Windows as well. I think it's the same command. So you're going to make this build directory, and then what you're going to have to do is you're going to have to change the permissions. Again, I don't actually know how to do this on Windows. But on Mac and Linux, you'll do change mode. You're going to add executable permissions to the user, and you're going to add this shell script. It's not malicious. You can read the whole thing. It enters that build directory. It calls a CMake command, which basically will generate this executable based on those files we're working with. Then it will call the make files that are generated in this build directory for you, and then it will call and run the executable. So I will show you really quickly what this looks like. So if we do /run, I've already done the change mode. It's going to generate all that, right? There's a warning right now because this is not actually returning anything, and it should. But as you can see, right, it builds and it's printing out what we expected from that driver function. So now it's up to you to go mess around and see what you can do. So yeah, make sure you're doing this, and then yeah, /run.sh, and do that from within the CPP folder. It'll get confused if you don't do it there. So yeah, make sure you do that. So that is the C++ version. I would spend more time on this because this is going to be more important as we move forward. This is really the model that we're going to be working with, but as a little fun extra exercise and a little foray into functional programming, I will say, let's go back to installs. You're going to need to make sure you have the Haskell, GHCI, I think it is, installed, and then you're going to need Haskell stack, because that's how we're running this whole thing. And you will go into this Haskell directory, so cd Haskell. No, that's not how you spell Haskell. Correct cat. Oh. Okay, there we go. Okay, so we're in here. So really the only thing you're worried about is this main.haskell file. All of this other stuff is just sort of build stuff that exists. You just focus on this file. That's all that matters to you. So what I've done is defined a template for you. So this is just importing some useful functions, right? You can check if something's a digit, if it's a space, if it's alphabetic, or if it's alphanumeric, right? We talked about that earlier. That should be super useful for you. I've defined all of the tokens here. So if you've never worked with Haskell before, try it out. It may be quite challenging, and I hope you'll learn something when we do the solution, but I'll just kind of walk through this. So basically, these are all tokens that I've defined, and then for some tokens, they're going to store a value. So for literals, right, you need to store the associated value. And for identifiers, you also need to store the value. And this just gives us the option, I believe, for printing and the quality operator, so we can do comparisons and printing of this later. Makes our lives a little bit easier. Then to make your lives easier when you work here later, I define this keyword so you can pattern match against this keyword instead of checking for each and every one. So you can check if a particular stream of input characters correspond to one of these and output that token fairly trivially. This is where you are going to be doing most of your work. So if you want a little bit of an example on my GitHub, which you can DM me on Discord for, I don't like to give it out because there's my name on it, etc. So I'm not just going to post it on YouTube, but if I can send you maybe a zip file of the project if you would like it. But I have sort of a not quite as robust as this will be or comprehensive, but it has a basic Lexer and Haskell, and it will give you an idea of what you're trying to do here. So this is where you're going to be doing most of your work in this Lexer function, and you'll be basically returning an array of tokens, but sort of that optional value is encoded in here for us. That's what's so great about Haskell. So as opposed to your Lexer, which might end up being a couple hundred lines of code, this may well end up under 100, which is really cool. Then this is where you'll basically call your Lexer from. You'll probably need to do some file input here. Again, that's in the basic Haskell Lexer I've already done, but I think you can probably fairly easily find how to do this online. I just have a very basic print function right now just so you can make sure it's working. So what you'll do here, let me add some directions again. We'll call those directions.txt. And what you will do is stack build and stack run in the Haskell directory whenever you want to run it. So show you right now. Oh, that is not a correct command. Okay, it built, and then stack run. There you go. It did. There will be more verbose output when you do it the first time, but I guess it's all cached on my machine because I just did it to make sure it worked. So yeah, right. So it prints this out. So yeah, please give both of these a shot. Talk about them in the Discord, and yeah, I'm excited to see what you all come up with. And please feel free to ask questions. This is hard. This is weird, and I tried my best to make this as clear as possible. But I know, the way I see it is not going to be the way some of you may see it. So please ask questions. I will respond to you as soon as I can. Ask each other questions. Everybody probably has great insight here. So yeah, work together, and I'm excited to see what we all come up with and work through my own problem-solving process on this in the next few weeks. I know that this was quite a long one, but thank you all who stuck around for sticking with it. I hope you learned something. I know I got a little bit rambly at times, but I wanted to try and convey as much information as I could to you. I hope that my templates are helpful. I hope the exercises really reinforce what we're talking about here. But please reach out if you have questions, and also talk to each other. That's where you'll really learn and expand on this. Please, there's a lot you can do with this. So probably get another. I think with how much is going on here, we might separate this out into 2 videos just based on how long today ended up being. Maybe we'll do the C++ Lexer and then the Haskell Lexer as a separate video in terms of my solutions, in the next few weeks. But yes, I will again link the Discord in the description. It's also in the channel description. Please join that. We have great community discussions, and now with these problems, it'll be a really great place to collaborate with everybody else who's working on this. So Again, please like, comment, and subscribe. And yeah, leave any feedback, please. Thank you again.